One of the main characteristics of metamaterial is negative permittivity and permeability. So it is very important to extract these parameters and analyze it. So in this video, we are going to see how these parameters can be extracted using CST. I have taken D.R. Smith's electromagnetic parameter retrieval from inhomogeneous metamaterial paper as the reference. I will put the link in description. I have started the CST and I'm going for new template. So our purpose is to simulate a periodic structure. So select periodic structure and it has different options like unit cell and full structure simulations. We are definitely going for unit cell and select it, and it has option for dispersion diagram and phase reflection diagram. So we know that the dispersion diagram is for surface wave propagation analysis. So we have to go for the phase reflection diagram, and you can see two different solvers like frequency domain and time domain. As we are going to consider the magnetic field, electric field excitations, it's better to go for time domain excitation. And in the next step, we have to verify that all the dimensions and the specifications are okay. So here dimension is in and wavelength and frequency is in and gigahertz. These are okay. So I'm going for next, and next I have to go for the frequency. And in the frequency, the paper, what the paper is like considering the frequency from. Okay, so I have to check what are the frequencies they have considered. So it is from 1 to 20. So I'm going to give 1 to 20 here, then finish. So it will set up everything here. You can see the time domain solver, and frequency, you can see 1 to 20 gigahertz is set up. So now our next aim is to means create this structure. So first we have to create the substrate and then these rings. So let's go for that. So for that, go for modeling and click box. So it will show that if you press escape, it will show the dialog box. So I'm going to create the substrate, and I'm giving the dimension using some parameters, and D is taken as, so this D is taken as the total dimension 2.5 mm. So this is the 2.5 mm. So I'm going to give minus D by 2 to D by 2 here, and Y minimum also the same. And for the substrate, the thickness is given by 0.25 mm. So I'm going to give Z minimum to Z maximum. I'm going to give the thickness. Oops. So this substrate, they have given us FR4 having the permittivity 4.4 and loss tangent 0.02. So let's see if we have that material. So I'm going to check if we have that FR4 material properties. So if I go for FR4, you can see that all the FR4 has a permittivity of 4.3, but in paper it is used 4.4 and low standard 0.02. So instead of using from the material library, it's better to create a new material. So you can create the new material here. So I'm going to give the material name as FR4, as I'm going to use it for SRR simulation. So I just given the name like here, and you have to give the type of the material as normal, and the permittivity is 4.4, and you have to go to the conductivity. Here you have to specify the tan delta. So the tan delta is 0.02. So I'm going to give 0.02 here. So I have considered the frequency from 1 to 20 gigahertz. So I'm giving the 10 gigahertz, that is the center frequency here. And you can click OK, then it will create the material. So here you can see the material property here. You can see that the permittivity and permeability values are as per whatever we have specified, and then click OK. So it will ask the value of D and thickness. D is 2.5 mm. Give the value, and thickness is like thickness of the substrate is like 0.25. So give the value 0.25. Okay. Then it will have created a substrate here. You can see the substrate here. Now our next step is to create the outer loop. So for that, I'm again going to the modeling, and I'm going to create the box. And so this loop I'm going to create here. You can see that dimension are L1 and L2. So what I'm going to do is I'm going to create a square and another square, and then subtract the squares. So the dimension of the squares are 2.2 and 1.8. So let's go. So I have given the outer, and So I'm giving the dimension of the outer square. So as it is created on the top of the substrate, we know that the thickness of the substrate is given as thick. So I'm going to give it as thick plus, and it also specify the PEC thickness of the metal is 0.017. So I have to give the thickness of 0.017 also here. That's what I'm giving here. So this is PEC. So L1 is 2.2. So L1 2.2. T is thickness of the metal 0.017. 0.017. Okay, so it has created the outer loop. Now I'm going to create the another solid again. For the subtraction purpose, I'm going to give it name as outer 2, and I'm going to give minus L2 by 2 to L2 by 2 minus. So I'm specifying the dimension here. So this is also the PC. Oh, sorry, here I have to give the plus. So the dimension of inner is 1.8. Okay, so now what I have to do is I have to subtract the this inner loop from the outer loop. So I'm going to select the outer loop, then I'm going for subtract, then select the inner loop. So it will be subtracting this thing. Next step is I have to create this gap. So this gap dimension is given as 0.3 mm. So as it is happening on L2 and L1 dimension, I'm going to create another square, and I'm going to give it as gap. And in X dimension, it is 0.3 mm gap. So I'm going to give like minus G1 by 2 to G1 by 2. And in along y-axis, we can see that it is in between outer and this loop. So it is in between L1 by 2 to L2 by 2. So I'm giving the thickness here. And this is also PEC. So let's see the preview. So I have to give the gap element. So here you can see that it's getting created. So what I'm going to do is I'm going to subtract the gap. So I have to subtract this one. So I have selected the outer and then subtract, then gap. So it has created the gap here. Next one is we have to create the inner loop. So I'm going to create the square again, and I'm giving the name as inner. So let's see what are the dimensions given. So it's L3 1.5. So I'm going to give as okay. So these are the dimension of that square. So L3 we have seen it's 1.5, right? 1.5. So I have given 1.5. So you can see another square is getting created. So our next step is to create one more square. So I'm giving the name as inner 2, and I'm going to give the dimension as L4. Okay, let's see what is the dimension of L4. It's 1.1. Okay, so I'm going to give the dimension as 1.1. Then click OK. So now I have to subtract inner 2 from that. So now we have got another loop. Next, our aim is to create a gap here. So for that, I'm going to create gap there. So it is in between L3 by 2 and L4 by 2. Oh, sorry. Oh, along the Y, it is minus L3 by 2 to minus L4 by 2, and here it is our gap G1. Yes. Okay. So here it is. Okay, so I have given. So now I'm going to subtract the gap. So we got the strips now, and now our purpose is to create a strip on the back. So that strip dimension is given by 0.14 and it is covering the entire dimension along the y-axis. So I have to create a strips along the entire y-axis. So I'm again going for the modeling and just give the name strip. So along x-axis, it's the width of that strip. So this is how I'm going for it. Along y-axis, it's the periodicity. So it is along the on the back. So you can give minus z minimum and the thickness of the PC. So that is you can give minus t. So you can give a preview. So if you give, it will be like this. Okay. I hope everything is okay. So now we have created both the strips. So I'm going to disable this working plane. So for better visibility. So you can see that now I have created the structure. So we have the substrate FR4 and inner and outer rings and the strips on the back. So everything is created. So our next step is we have to provide the boundary. So for simulating this structure, we have to provide the boundary. So let's see how this boundary we have to set. So in case of split ring resonator, the arrangement will be like this so that you can see that there is some gap between every layers. So if you consider X and Y and Z in this axis, you can see that along Z axis, there is some gap between each layers and this is periodic in this directions. So this means that if we have to consider a unit cell, we have to give some spacing on both plus Z axis and minus Z axis. So that means we have to give some spacing in plus and minus Z axis. And in our previous video, we have seen that if the magnetic field has to excite these loops, this magnetic field has to be perpendicular to these loops. That means that as these loops are in these directions, we have to align the magnetic field in front and back of these loops. That means along Z axis, we have to provide the magnetic boundary. That's why it's here. So we have to provide some space along Z axis and we have to provide the magnetic field along the Z axis. And for the strip is actually excited by the electric field. So for that, we have to apply the electric field along this strip. So as these strips are in these directions, we have to provide electric field here and here. That is along the y-axis, we have to provide the electric field. That's why y minimum and y maximum are the electric field. And we are considering the incident field along this direction. That means that we have to consider the electric field along x-axis. That's why we are given the boundary condition open, open here. So we are going to assign the port on the x-axis. This is how the boundary has to be assigned for the SRR material parameter extraction. So this is just a modified view to see it correctly. So along Z axis, we have to provide some spacing and we have to give the magnetic field boundary. And here, Y axis, we have to provide the electric field boundary. And X axis, we have to provide the open boundary conditions. So this shows how we can assign the gap along Z axis because we have to provide some gap along the Z axis because that's how the unit cell is arranged in the SRR structure. So to assign that, we can use the background property step and we can assign the distance like this because in lower and upper Z directions, we can give the spacing like this. So this is how it has to be done. Oh, sorry. And now we are going back to the CST simulation. So now we have done this thing. So now I'm going to do the background. So in background, my aim is to provide some distance along the lower and upper. So I have given some spacing, then I have given the spacing here. Then in boundaries, I'm going to, so we have seen that in Z, we have to provide magnetic field. So I'm going to give the magnetic field on Z axis and X axis, we are, oh, sorry, Y axis, we have to give the electric field. So you can see that this is the y-axis. That means the along the strip we are going to give the electric field. And perpendicular to this loop, that is along z-axis, we have given the magnetic. And along this axis, what we have to do is we have to provide the excitation. So I am giving the boundary open. That's how this boundary is. So we have provided open boundary along x, and along y-axis we have given the electric field as this is the direction of the strip, and perpendicular to the loop we have assigned the magnetic field. Okay, so now how it is looking. Okay, so this gap we have provided using the background settings. Next, now this, so we have to assign the port here. So I'm going to assign the port like new waveguide port. So it is along x-axis, so it automatically detects that. So I'm going to check everything, and I'm just going to consider only one mode of simulation here and click OK. Next, we have to create another port. So we have to create another port on the opposite side. So I'm giving X negative. So it will create the port here. So you can see how the ports are assigned. Here also I'm considering only one port. So set OK. So we have two ports along the X axis, port 1 and port 2. And our next step is to check the mesh settings. So before going that, so this is how we can set the mesh using the global properties. So here I am giving the cell per wavelength as 10, but for better accuracy, you can always increase to like 15. So if you give 15, it will be more and more accurate. And I'm going to simulate it, and I have selected hexagonal FIT, and I'm going to simulate all the ports and all the modes. As I have set only one mode, it's going to simulate for only one port, and I just start the simulation. So it will be running the simulation. I think it will take only less time. I'm going to, okay, our simulation is complete now. So now we are going to check the S parameter. Here you can, so we are going to check both S11 and S12. So here is S11 and S21. So what I am going to do is I am going to check the linear value of that result, because in the report, means in the paper, it's given as the linear value. Here you can see that S11 and S12. So this trend is all same as whatever is given in the paper. So whatever S11 and S12 given in the paper, we have simulated using the CST. And our next step is to extract the permittivity and permeability. So now we have extracted the S11 and S12 to extract the permittivity and permeability. You can go to the post-processing. So CST has inbuilt macros to create the permittivity and permeability from these S parameters. So here you can go for the S parameters, then go for extract permittivity and permeability from S parameters. So when you select that, you will get a window like this. You can select S parameter. So whatever the result we have simulated, all the result will be listed here. So you can select whichever S11 you want to give for the parametric extraction. You can give it here, and S21. So I'm giving S21 also here. And this is the effective thickness of the material sample. So I will show you how you have to take the thickness. Means we are giving, so we know that the thickness of the substrate is 0.25, but here we have given the port excitation because this is our incident wave. So we have given the port along these dimensions. So this becomes our thickness. That means the total thickness is this total dimension, that is the 2.5 mm. That is how we have to give the thickness, not just the thickness of the substrate, but the thickness coming in between these two ports. So here we have to give 2.5 mm, then click OK, then select this and evaluate. Okay, so if you go to the tables, you can see the extracted parameter epsilon r mu r like this one. So I'm going to take the mu parameters, and what I'm going to do is I have to take, because in paper it's given both the real and imaginary. So to get the real and imaginary, click here. So you are getting both the real. This solid line shows the real permeability and the dotted line shows the imaginary permeability. So here you can see that this is also showing the same trend. So we have extracted the permeability using the CST. Similarly, for epsilon r also, you can extract real and imaginary values in the paper. Like here you can see that it is actually plotted from 5 to 15 gigahertz. So if you want to see from 5 to 15, you can go to plot properties. Instead of auto range, you can give the frequency as 5 to 15. And okay, so that we have given along y-axis, it may be from 2 to minus 20. So if you can give that also in y-axis. So I'm going to give minus 20 to here. So you can see that this is also following the same trend as the paper. So now we have extracted the permittivity and permeability. So here my interest is permeability. So you can see that the imaginary part of the permeability is becoming high at this one, and this is our resonant frequency. So I may, because in our previous video we have seen that this is the permeability curve that will be we getting from an SRR structure, and at the resonant frequency the permeability of the imaginary permeability will be very high, and this is the real permeability. You can see that below the resonance the real value of permeability will be positive, and after the resonance it will be negative, and then it get increased to positive. So this is the trend we have to expect. Similarly, here also we can see that at resonant frequency, the imaginary part of the permeability is getting high, and above resonance, the real part of the permeability is positive, and just above resonance, the imaginary part becomes negative and it becomes increased to the positive. So this is our area of interest where the SRR shows the negative permeability. Similarly, we can also see that the permittivity is also showing the negative values here. And so that's all. So in this video, we have seen how we can extract the material parameters from SRR. So you can do the same for any metamaterial structures. So you have to be careful how you have to assign the boundary conditions. So you have to check the whole picture of the entire structure, and based on that, you can do the simulation and extract the parameters. Thank you everyone for listening. If you have any doubts, please feel free to share in the comment below.